Hi, in this video we will learn a generalization of vectors in the plane. In the plane, the vectors and points, they had only two components, but we can have vectors with n components. That is called the space Rn. We will see that vectors with n components also have the operations we define for vectors in the plane, and we will study the properties of those operations. So let me start with the point that first thing, we are working with real numbers, all rational and irrational numbers. The notation we use for this is R, and our components in the plane, and so far everything we have worked with are real numbers. So remember that every a component of vectors in the plane are real. In other words, we have been using two copies of R to fix our vectors in the plane. So that's why we choose the notation R to the power 2. Vectors with two components. In general, vectors with n components can be studied. Remember that the order of the components are important, and they have the first one, the second one, and so on. So we are basically we are going to be to study the ordered n tuples, and these ones, something like this, you would have u1, u2 up to un. This is in row notation, and then in the column version also we'll have u1, u2 up to un. Okay. This is also column version, and you'll see me using both of them. The set of all such vectors is denoted by, well, again, the components are coming from real numbers, so that's why we have real, to the power how many components, that's there, Rn. So that's where that name comes in, R to the power n. And when you have those ones, you can study the operations. How we can do operations for vectors with n components. Well, remember the keyword was component-wise. All the operations were done component-wise. So everything we can generalize. So, for example, addition, vector addition would be, well, if I add u1, u2 up to un to v1, v2 up to vn, this is, well, you add the first component, u1 to v1, u2 to v2, and up to n, un plus vn. Scalar multiplication, well, you multiply a constant to vector u1, u2 up to un. Remember, components wise, so it will be multiplied to all of the components. Then negative vector, you remember minus u, if u is u1 up to un, is negative u1 negative u2 and goes up to negative un. And then as the last one, this was subtraction, which was, okay, if I have u minus v, then first component of u minus first component of v, second component minus second component, and this goes to un minus vn. Remember, everything is possible because of this generalization based on the component wise operations. All these operations are component wise, so we can easily generalize them. What about the properties? Most of the properties that the numbers have will carry over for vectors, at least for the case of addition and scalar multiplication and subtraction goes. So for example, if you have a vector u, you wanted to add to v, this would be the same thing as if you add v to u. Well, why is this case? Because when you add u to v, this is why? Because if you add u to v, so you have u1, u2 up to un added to v1, v2 up to vn, yes? Then this gives us u1 plus v1, u2 plus v2, and this goes to un plus vn. Now that it's down to the components, these are just numbers. In the numbers, a number added to another one is the same thing as the second number added to the first one. 1 plus 2 is the same thing as 2 plus 1. And here we can switch the orders, so we can get 1, v1 plus u1, v2 plus u2, and up to vn plus un. And this is the same thing as v added to u. So this shows that when you do the operations, when it goes to the components, if the components have a property, it can be transferred to the operations of the vector itself. This property is important one, and it has a name. It's called commutativity, or vector addition is commutative. The second property is an interesting property. So we have learned that we can add two vectors, u plus v. How about if I have a third one? How can I make sense of this u plus v plus w? Well, okay, you say, I know how to add two of them. Let's just group two first and then add to the third one. Very nice, we can do this. But how about if someone comes and does the other way around? So, I mean, another grouping. So, for example, it does this thing first. Would these give us the same result? And the answer is yes. This is called associativity. And as you can see, this is true for numbers. So if you have two numbers, three numbers added, you can do two first, then add to the third one, or you can add two last one and then add it to the first one. These property can be these properties can be proven like the one that I proved in the case 1, commutativity. Exactly same thing. So you start from left hand side, go to the components. In the components you have associativity, so you can do the operation for that property on the component, and then get back to the vector version, and you will see that this happens. What else? What other properties we have? Well, for example, we have something about the scalar multiplication and vectors. So if I multiply c to u plus v. So scalar multiplication distributes over the sums of the vector addition. So it will be cu plus cv. Also, the other way around is true. So vector scalar multiplication distributes over the sums of scalars. So here, like this, and this will be cu plus du. Both of these properties all are called distributivity. So vectors addition is commutative, associative, and distributive. Well, there are other properties also. For example, if we add any vector to zero vector, well, it means that every component is being added to zero. So zero doesn't change number, you get u back. Also, we know that if you add a vector to its negative, they basically cancel each other component wise, and then at the end you get zero vector. Also, there's this nice property that when you multiply number zero, scalar multiply to you get a vector whose components are all multiplied by zero. So you get a vector full zero, and that is zero vector. Or if you multiply the number 1 to a vector, you get all components exactly as before, and you get this value. So these are the properties. One more property, there's one more. Let me add that one also. When you have two scalar numbers, you can first multiply, then scalar multiplication, or you can start with one of these scalar multiplications, and then you get a vector and do a scalar multiplication again. So these are different order of doing this thing, but this is also true, and we will have all these nice properties. You can now prove these properties just by doing some of these tricks that I showed in this proof. Well, what does this properties have for us? These properties will give us the tool or all the requirements to be able to deal with vectors as if they are numbers, because these are good properties of numbers, at least when it comes to these operations. Well, what I mean, I can show you in an example. Find next which satisfies the equation 2 times x minus 3 times 1 to 4 equals 0 vector plus 2 times negative 1, 1, 1. So this is an equation that you have here, but the variable here is a vector. How we can solve this? So let's just use the property 2x minus 3, 1, 2, 4 equals to 0 plus 2 times negative 1, 1, 1. Very nice. So here, 0 vector added to anything, the right hand side will be again 2, negative 1, 1. And this will be 3, 1, 2, 4. 2x. This is the property. Add 0 vector to any vector here, you get the same vector back. Then we can apply the scalar multiplication. So scalar multiplication here, oops. Scalar multiplication here gives us minus 3, 6, and 12 equals to negative 2, 2, and 2. Oops, and 2. How can I take this to the other side? Well, even in the numbers case, if you have 2x plus 1 equals to 3, the way in practice we do this thing, taking 1 to the other side, is that we add both sides the negative of the number we want to take to the right hand side. So it will be 2x plus 1 minus 1 equals to 3 minus 1. Yes, and then this guy is 0, and this gives us 2x plus 0 equals to 2. We apply exactly same kind of thing. We add the negative of this whole vector. So negative of that is plus 3, 6, 12. So we add to that both sides, and then that gives us 2x minus 3, 6 plus 12, oops, and 12 plus 3, 6, 12 equals to negative 2, 2, oops. And 2, and both sides are added, this vector. Okay, so this vector plus its negative, remember that a vector plus its negative is always a 0. So this gives us 2x plus 0 vector is equal to, well, that's just vector addition. So we will get minus 2 plus 3, 2 plus 6, 2 plus 12. And then 2x, any vector added to 0 vector is the vector itself. So it will be 1, 8, and 14. How we can get rid of 2 here? Look at in the class, in the scalar case, 2x is equal to 2. How do we take this 2 to the other side? The way we do it is multiply both sides by the inverse of the number. Here's 1 over 2. So 1 over 2 times 2x equals to 1 over 2 times 2. And then these two cancel. Well, after applying the associativity of product, you get 1 times x is equal to 1, and then 1 times x is x. So that's how we solve it. Here also we do the exact same thing. Multiply both sides by the inverse of 2. So you get half of 2x equals to half of 1, 8, 14. Then remember that if you have two scalar numbers multiplied, you can first multiply those scalar numbers. So here we can do half times 2 first, then multiply by x. And this will give us half times 1, half times 8, and half times 14. These two cancel, you get 1 times x equals to half, 4, and 7. And 1 times a vector is that vector, and this is how we solve this equation for the vectors just by basic properties of the vectors in, well, in this case R3, but in general you can do exactly the same work in Rn. Okay, very quick wrap up. We learned that in we can work with vectors with n components, and the vector operations are again component wise defined, and they have good property. These properties can be used in solving vector equations.